Good morning, everyone. Before we start chapter 4, does anyone have any question on chapter 3? So we have done spring elements, bar elements, truss elements, and now we are ready to move to beam elements. And this is going to be what we're going to be doing in chapter 4. So we're going to follow the steps to formulate the beam equations so we can get a beam element stiffness matrix. But before we do that, I would like to take the first few minutes of the class to review the beam theory and what we have established from solid mechanics and the beam differential equations, so we can use them later. Last class period, we talked about the bar differential equation, and I did not go through the derivation, but I think when you see the beam elements, you will see that the bar element differential equations are easier to develop. So this is the beginning of chapter 4, where we're going to development of beam equations. So just to refresh, a beam in general is a long cylinder, typically long cylinder structure, remember, that is generally subjected to transverse loads, right? And when I say transverse loading here, they're perpendicular to its axis, right? And these transverse loads, perpendicular to the axis of the beam, would produce significant bending effect as opposed to twisting or axial stresses. And you notice here the wording about generally subjected to transverse loading and significant bending, because we can have short beams, right? We can have beams that are subject also to a moment. The idea here, we are focusing on this bending effect. So if we're going to look at a beam element in its simplest form, so just having two nodes, node 1 and node 2, and having a length L, and we are working here in the XY plane and the axis of the beams. You can think of these as local axis. So the x-axis is oriented along the axis of the beam. How many degrees of freedom do we expect to see? Like when this goes in bending, it can deform something like this. depending on the loading. So how would I describe degrees of freedom at the nodes? As a matter of fact, of course, what I'm showing here, it's as if it is restrained from translation in the y direction, correct? But along the length of the beam, you see that there is translation in the y direction, correct? So primarily, we have degrees of freedom of a translation in the transverse direction, where the beam, in the same direction the beam is expected to be loaded, as well as rotation. And when I'm working in the XY plane, this rotation is going to be about the z-axis. Usually when we're working in plane, we refer to it as clockwise, counterclockwise, because it's all about the same axis, the z-axis, right? So I can put 2 degrees of freedom per node, total of 4 degrees of freedom.
But I don't know whether maximum time, does it mean sometimes the type of fixed condition or something affect the number of degrees, or is not applying to the normal structural thing?
The end conditions are going to be considered as constraints, if you do have them, right? Is that what you mean?
Yes, but I remember there's a type of support, maybe support for the bar could be roller or for the bar. So I think it won't it affect the number of the degrees of freedom?
When we start solving, but when we are deriving element equations, no. And that's why I said this red curve is not the best representation, because really this red curve that I'm showing, in a way, I'm restraining translation in the y direction, which is not right, correct? So if I'm thinking freely about degrees of freedom, I would think here, like at node 1, I would have a v1 in the y direction. At node 2, I will have a v2. At node 1 also, I do have a rotation that I can refer to as phi1. And at node 2, I also have a rotation I refer to as phi2. And please note the positive sign convention. Degrees of freedom are positive translational when they are moving in the positive y direction upwards, and the rotation when I have a clockwise right-hand rule, z-axis perpendicular. So that's why the counterclockwise is considered positive. Now, corresponding to these degrees of freedom, we are going to have nodal forces that we usually solve for, right? So with V1, I'm going to have F1y. With V2, I'm going to have F2y. With Phi1, I'm going to have an M1. And corresponding to Phi2, I'm going to have an M2. So what I am showing here is a beam element with positive nodal displacements. Right? So this is really the objective here of establishing these positive nodal displacements. And when I say displacement, typically I mean translational and rotational degrees of freedom. In this case here, I'm using V's and M's, right? V's and P's, sorry. As well as nodal forces. And this would include forces and moments, represented here by V's and M's. So V i's here would represent the local transverse nodal displacement. The phi i's represent the nodal for the VI's, I really mean this is nodal, not local. So the VI's represent the nodal transverse. I have nodal here. Okay, so this is local. Local transverse nodal displacement, and the VI's represent the nodal rotations. The F1, or sorry, FI Y's here, this would represent local transverse nodal forces. Because we are working in plane, for the rotation, the local would be the same as global, right? So that's why with the rotation, I'm not mentioning local or global.
You represented the forces as V's.
The forces as F, the green.
Yeah, in Y you said another forces, the bracket moments, and then you
Oh, I'm sorry. Thank you for catching this. Okay, F's, yeah. And finally, M I's, they represent the nodal moments. So again, one of the main objectives of this is to show the positive directions for nodal displacements and nodal forces. Before I move forward, I want to compare these to our sign convention that we used with the beam theory. So when we developed the beam theory, sign convention for shear forces and bending moments. If I look at a similar, or look at the element here, where it's as if I am looking at a section to the left of the beam or section to the right of the beam. If this still has a length L, a positive shear to the left of the beam will be going upwards, correct? And we refer to this as a shear force uppercase V. How about the shear force to the right of the beam? Positive will be going downwards. Positive bending moment is always putting tension at the bottom, compression at the top. So this would be a positive moment. This would be a positive moment. So this is the positive sign convention for V and M. And you may recall when we worked on bar elements, it was also important to compare how the tension relates to local forces on both ends. Because the local forces were always positive going in the x direction for the element. But of course, tension was pulling in opposite directions at the two ends. So we're going to remember this. We are going to look at the Euler Bernoulli's beam theory. So if I look at a beam, along the x-axis, this is the y direction, and this is where I also measure v, the displacement. Now, this beam may be subject to any distributed loading in the transverse direction. So any function here, w of x. And of course, it could be supported to resist this downward force. What we are going to look at, we are going to look at a differential beam element, A, B, C, D. And what I'm doing here is I'm looking at sections that are perpendicular to the centroidal axis of the beam. As a result of the load, the beam will go in bending. Now, if I look at my infinitesimal element, after deformation, the A will become A prime, C will become C prime, D will become D prime, and B will become B prime. And if I compare that to the original direction, you will notice that we get this angle phi. What did the beam theory states? That the plane cross section perpendicular to the longitudinal centroidal axis of the beam before bending remain plane. So this green line remain to be a plane and remains to be perpendicular to the axis after bending. So if I show the centroidal axis like this, here the centroidal axis or the deformed axis will be going like this, where these are still 90-degree angles. So this is what the beam theory stated. You remember that? Plane axis before bending and the plane axis after bending. If we look at this infinitesimal or differential beam element, so we were cutting through the beam. And I'm going to consider this part of the length as dx. It is subject to that distributed load W of x. And when I cut this section of the beam, I'm going to need to show the internal forces. So on the left side, I'm going to get this shear force V and bending moment M using the positive sign convention. And if I refer to this as 1 and this is 2, at 2, I am going to get a V plus dV. And I'm also going to get an M plus dm. If we write equations of equilibrium, sum of the forces in the y direction is equal to 0, and I take upwards as positive, I can show that V minus V plus dV minus the W of x dx is equal to 0. So I get from this that minus W of x dx minus dV is equal to 0, or dV by dx is equal to minus W of x, given the load is going downwards. And if you recall, this was a relationship we used when we were sketching the shear diagrams. Next, if I do sum of the moment is equal to 0 for this infinitesimal element, and I can take that sum of the moment about either 0.1 or 0.2. If we take it here, and let's say we're going to take the counterclockwise as positive, I can go like minus M minus, so I'll be taking the moments about 0.2. So I have V dx also. And then I have the M plus dm. And the moment from the distributed load would be a plus W of x dx times dx over 2. So we're taking moment about 2. This is equal to 0. So again, when we simplify here, minus M and M are going to be gone. So I'm left with a minus V dx plus dm plus W of x over 2 dx squared is equal to 0. Oh, yeah, minus V. Yeah. And we have dV by dx equal to minus W of x. So we can show here that dm by dx is equal to V. And this was the relationship we used. The slope of the moment at any point is equal to the shear force. I also want to remind you that when we looked at the curvature of the beam, if this is the x-axis, when the beam deforms, we get this curved elastic curve, and this curvature has a radius rho, and if I draw a tangent to the curve, I can be looking at this same angle that we defined phi. The inverse of the radius of curvature is known as the curvature. So 1 over rho, if I call this as k, this 1 over rho is equal to m over EI. And of course, we proved that in solid mechanics. From the math, we also know that the curvature k is equal to d2 little v by dx squared. For a small deformation, phi is equal to dv by dx. And when I look at this, I can write that m is equal to EI d2v by dx squared. Correct. Here. This is from calculus, by the way, based on curvature. Now, v is equal to dm by dx. So if I solve for v, basically taking the derivative of EI d2 small v by dx squared. Now, the derivative of v is equal to minus wex. So if I take dv by dx, that would be d squared by dx squared of EI d2v by dx squared. This is equal to minus w of x. If EI is a constant, we can pull it outside and say that EI d4v by dx to the power 4 is equal to minus w of x. So this would be the beam differential equation should EI be equal to constant. When we are looking at a beam element, with only nodal forces, no distributed load W. So W of x is equal to 0. Then EI times d4v by dx to the power 4 would be equal to 0. So this would be the beam element differential equation. I'm sorry. Of course, I had here E and I. Just recall that E is the modulus of elasticity. And of course, we are looking at linear elastic behavior, right? Modulus of elasticity. And I is the moment of inertia about the neutral axis. Right? Of the section. And the neutral axis of the section is the centroidal axis in the same direction of bending. This is how we find the neutral axis. So for example, if I have this kind of section, the centroid will be here. If I'm looking at, this is like a side view, this is my beam along the x-axis. And if I cut here and look at a section, this is what my section look like. If the beam is bending about the z direction, so this would be the neutral axis, z, and it is the neutral axis, going through the centroid in the same direction as bending. So this is z, and this is m. So this is, sorry, this is y. So this is for a beam that bends about the z-axis. Which one is the neutral axis? Is the red one. Okay, which by the way is in the z direction. Okay, I think with this background, we are ready to move on to the beam element equations. And we're going to follow the steps that we established. So number one would be to select the element type. Beam element. So we have these two node elements, 1 and 2. The length is L, and we have 4 degrees of freedom as established. V1, V2, V1, V2. So these are 2 degrees of freedom per node. We have 2 nodes, 1 and 2, for the element. So we have 4 degrees of freedom total. Step number 2, we want to select a displacement function.
These two is both V and A face in the same direction.
V1 and V2 are in the same direction, which is the positive y direction, right? So we're working the local directions here would be X and Y. V1 and V2 are perpendicular to the axis of the beam, which is oriented along the X axis. Now, when I look at the beam element, I have 4 degrees of freedom total. So we're gonna choose a cubic displacement function. So what is this going to look like? Now, of course, when I mention here displacement, as we looked at the beam, the displaced shape of the beam may look something like this. Where you see here, I have a V1, here I have a V2, and at each of them, I do have an angle. Okay. Now, when I look at this displaced shape of the beam, what kind of function is needed to describe that? Like, I'll rephrase the question. When we looked at beam deformation, we had some equations in the back of the book that we used to go to, and they would give us the equation of the elastic curve, of this green curve here. So this is function, a V function, or V as a function of X. That would give me that green curve, right? So when I'm referring here to a displacement function, that would be a V of X. And when I say I'm going to use a cubic displacement function, I'm going to write this V of X as A1 X cubed plus A2 X squared plus A3 X plus A4. So when we had 4 degrees of freedom, we have these 4 parameters corresponding to the 4 degrees of freedom to solve for. So this is why our polynomial is a 3rd degree polynomial, or we picked a cubic function. In order to solve for A1, A2, and A3, and A4, I'm going to express the nodal degrees of freedom using V of X. So I'm going to look at V of 0, and I'm going to say, oh, this V of 0 is equal to what? Is equal to V1, correct? Now, when I substitute here for X equals 0, I will conclude that A4 is equal to V1, correct? Next, if I look at Phi1, I can describe that as dV by dx at x equals 0 is equal to Phi1. If I take the derivative and substitute for x equals 0, I can easily show that A3 is equal to Phi1. Next, if I evaluate V at x equals L, this would be V2. When I write this equation, which is A1 L cubed plus A2 L squared plus A3 I already solved for A3, so I can write it as phi1x plus A4, which is V1. Right? Then if I do dv, these are all lowercase v's, by the way. Dv by dx at x equal L, this would be equal to phi2 here. Okay, so phi2. If I take the first derivative and substitute for x equal L, I will have 3a1 L squared plus 2a2 L plus A3, which is phi1. Now we can solve these two equations together to find A1 and A2. So if I refer to this as 1 and 2, I can say that from 1 and 2, we can find that A1 is equal to 2 over L cubed multiplied by V1 minus V2 plus 1 over L squared multiplied by phi1 plus phi2. And A2 will be equal to minus 3 over L squared times V1 minus V2 minus 1 over L times 2 phi1 plus phi2. So having solved for A1, A2, A3, and A4, I can come back and express the displacement function in terms of nodal degrees of freedom. So now we can express v of x as a function of nodal degrees of freedom. So this v of x, if I substitute here a1, so I'm going to put 2 over L cubed v1 minus v2 plus 1 over L squared phi1 plus phi2 multiplied by x cubed plus minus 3 over L squared v1 minus v2 minus 1 over L 2 phi1 plus phi2. This is times x squared plus a3x plus a4. A3 is phi1, so I get here plus phi1 times x plus v1. Now I can rewrite this displacement function or express, just rearrange. I can write v of x as equal to 1 over L cubed 2x cubed minus 3x squared L plus L cubed times V1 plus 1 over L cubed x cubed L minus 2 x squared L squared plus x L cubed times V2, I'm sorry, V2, V1, sorry, V1 plus 1 over L cubed times minus 2x cubed plus 3x squared L multiplied by V2 plus 1 over L cubed multiplied by x cubed L minus x squared L squared. This is multiplied by V2. So now you can see clearly, I have here the 4 nodal degrees of freedom. And I have here some functions of x and L. L is constant and x is the only one that is changing. So what does this remind us with? Shape functions, right? So in matrix form, we can relate this V of x to the nodal displacements V1, V1, V2, and V2 via 4 shape functions, N1, N2, N3, and N4. So I can simplify this as N row matrix times D column matrix. So I have here a 1 by 4 times a 4 by 1. Where you can see clearly, this is N1, this is N2, this is N3, this is N4. But from what we learned about shape functions, if I sketch N1, which is equal to this 1 over L cubed times 2x cubed minus 3x squared L plus L1. Oops, L1. No, there is no L1. I'm sorry, L cubed here. Okay, if I sketch this function over the length L between the 2 nodes, so this is my x direction. At x equals 0, I get L cubed over L cubed. So I will get here a 1. If I continue to plot this function, at x equal L, you will find that N1 is equal to 0. And it must be so. If I solve for phi1, it also must be equal to 0. And phi2 must be equal to 0. Therefore, this function is going to look something like this. If I look at N2, 1 over L cubed times x cubed L minus 2x squared L squared plus xL cubed. I want to clarify here or emphasize that with a shape function corresponding to degree of freedom 1, it has to have nodal degrees of freedom equal to 0 anywhere except the first degree of freedom. So this is why phi1 is a 0, phi2 is a 0, v2 is a 0, but only v1 is equal to 1. When I look at N2, This corresponds to the second degree of freedom. So when I plot this function, V1 is going to be equal to 0, but phi1 will be equal to 1. So if I substitute for x here equals to 0, I will get a 1. If I continue to plot the function, I'm sorry, if you select x equals 0, you get a 0, right? But if you substitute in this function for x equal L, you will get a 0 also. So I have a 0 here and a 0 here. But when you sketch the curve, it's going to look something like this. What does that mean here? I have an angle phi1 equals to 1, where V1 is 0, V2 is 0, and phi2 is 0. Maybe I should write the same here. V2 is 0, phi2 is 0, and phi1 is a 0. Maybe that clarifies it. So you see the shape functions, first two. If I continue for the third and fourth, N3 is here. So I have 1 over L cubed multiplied by minus 2x cubed plus 3x squared L. And let's plot this function. At x equals 0 is going to be equal to 0. At x equals to L, we're going to get a 1. So it's going to be equal to 1 here and 0. So I have a V2 equal to 1, phi2 equal to 0, and V1 must be a 0, and phi1 also is 0. So it's going to look like this. And finally, N4 is equal to this last term, the fourth term, 1 over L cubed times x cubed L minus x squared L squared. So if I plot this function, at x equals 0, I will get a 0. At x equal L, I will also get a 0. So that tells us that V1 is a 0, V2 is a 0. Phi1 must be a 0, but phi2 now is going to be equal to 1. So this is going to look like this, where this angle here, phi2 is equal to 1. N1, N2, N3, and N4 are the shape functions of a beam element. The cubic, if you look at them, they're all cubic functions, right? The cubic shape functions are known as the Hermite cubic interpolation functions or cubic spline functions. So this was step 2, where we were able to express or write displacement functions using nodal displacement and shift functions. If anyone still writing? Step number 3 would be to derive some relations, right? We're going to derive the strain displacement and stress strain relations. Relationships. So simply, if I'm looking at a section of the beam, and this is my neutral axis, if the beam is in tension, is going to elongate at the bottom and compress at the top. And this plane section before deformation would remain plane after deformation. This is the neutral axis, right? And this is a section. So what I'm looking at, of course, more correctly, it's a neutral surface, not a neutral axis. And if bending is happening in about the z-axis, the neutral surface would be in the xz plane. Does that make sense? So, okay, let me try to sketch that. If I'm looking here at the beam, if this is a rectangular section, so this is my centroid, and this would be the axis of the beam along x. Right? If the beam is bending or is subject to a bending moment about the z direction, because this is the y direction. So this is the direction of bending. Okay. More accurately, we have a neutral surface that goes like this. This green one here. If I'm looking at a cross section, I may refer to this as the neutral axis. If I'm looking at the direction along the x-axis, like what I'm doing here, I'm referring to the x. So this, referring to this as the neutral axis, or this as the neutral axis, depending on how I'm looking at it. So here I'm looking at this is the x direction. If I'm looking at a section like this, where this is y and this is z, I would also refer to this as the neutral axis. Make sense? Okay. So when I'm looking at this deformed section, we said that this angle is going to be equal to the slope of the curve, or phi. This phi equal to the slope of the curve, so equal to dv by dx. If I'm measuring y up, like this, so if I go a negative y, this would correspond to this elongation. So if I consider this as the elongation, if I know this minus y, and if this angle is very small, so this would be equal to minus y 10 phi. So I can say here that u is equal to minus y 10 phi. And what is epsilon x? Epsilon x is du by dx. So u is equal to minus y 10 phi for small angles. For small angles, we can say that 10 phi is approximately equal to phi. And phi is equal to dv by dx. So I come here in this equation. If I substitute for 10 phi with phi, so I'm going to say, therefore, u would be equal to minus y times phi, or minus y dv by dx. Now, if I take the derivative of this, I would say that epsilon x would be equal to minus y d2v by dx squared. So this is a relationship between the strain and the displacement v. We said also we're going to do a stress strain relationship. For linear elastic behavior, sigma is equal to E times epsilon. If I substitute for epsilon, so sigma x equal to E times epsilon x. So I get a minus E times y d2v by dx squared. From the beam theory, we also found that sigma x is equal to minus m over y times, over I times y. If I set these two to be equal to each other, I can write that minus E times y d2v by dx squared is equal to minus m over I times y. So the y's are going to cancel together. If I solve for m, I will get that m is equal to, and of course there are two negative signs here, I get that m is equal to EI times d2v by dx squared. And by the way, we can use this to evaluate m along the axis of the beam for any given x. Want to remind you that dm by dx is also equal to v. So if I take the derivative with respect to x, I can write that v is equal to EI d cubed v by dx cubed. So this will give me the bending moment and shear at any x. So I can write it here as m of x is equal to EI d2v by dx squared, and v as a function of x, I want to keep this uppercase v, is equal to EI d cubed v by dx cubed. Okay, step number 4. We want to now derive the beam element stiffness matrix or stiffness equations. So if I look at my beam element, length L, and I have 2 degrees of freedom. I have nodal forces here, F1y, F2y, and I have here M1, and I have here M2. And please note that I am following the element sign convention. Positive moment is counterclockwise. Positive transverse loads is in the positive y direction. Now, in order for us to write the element stiffness matrix or element stiffness equations, I am going to use the equations from the relationships to evaluate the nodal forces. Okay, so we're going to use the equations we just derived to evaluate the nodal forces. Use derived equations to evaluate nodal forces. So if I evaluate F1 of y, okay, so F1 of y is in the same direction as the positive shear. So I can directly come and use V of x and substitute for x to be equal to 0. So F1 of y is equal to V of 0. And for the sake of time, I'm going to be skipping some steps, but the concept, I think, is straightforward. So I have here equal to EI d cubed lowercase v by dx cubed evaluated at x equal to 0. So when by the way, we already have v, right? So we have v expressed as a function of x. So we can take the third derivative, right? We can take the third derivative for v. So when I do that, I will get EI and substitute for x equal to 0. EI over L cubed times 12 V1 plus 6 L phi1 minus 12 V2 plus 6 L phi2. Then we're going to solve for M1 here. And M1, I'm going to use the moment equation. So I'm going to have evaluate. Yeah, before I start, please pay attention to the direction here. This is counterclockwise. According to my moment convention, this is putting compression at the bottom. So it's negative. It's a negative bending moment. So I'm going to throw in a negative sign and then start using m of x. So minus m of x is 0. That would mean I'm going to use a minus EI. And here I have d2v by dx squared. And I'm going to evaluate that at x equals 0. It's a straightforward math, by the way. When I do the evaluation, I get EI divided by L cubed multiplied by 6L V1 plus 4L squared V1 minus 6L V2 plus 2L squared V2. Next, we'll do F2Y. Positive is a positive shear to the right end of the beam, going up or going down? Going down, right? The first thing we did today, this is a positive shear, right? So I'm going to throw in a negative sign. So I'm going to say minus V of L, which is equal to minus EI d3V by dx cubed evaluated at x equal L. And I get here an EI over L cubed multiplied by minus 12 V1 minus 6 L V1 plus 12 V2 minus 6 L V2. And lastly, M2 is equal to counterclockwise moment, putting tension at the bottom, compression at the top. It is a positive bending moment. So I don't need to put a negative sign. For M2, I'm going to use M at L, which is equal to EI d2V by dx squared evaluated at x equals L. EI over L cubed multiplied by 6L V1 plus 2L squared V1 plus 6, sorry, this is a minus, 6L V2 plus 4L squared V2. I have here 4 equations that relates F1Y, M1, F2Y, and M2 to the nodal displacements V1, V1, V2, and V2. I can take EI over L cubed as a common factor and start putting the elements of this matrix. I will get here a 12, a 6L, a minus 12, and the 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, and 4L squared. This here can be simplified as F equals to K times D. F is a 4 by 1, K is a 4 by 4, and D is a 4 by 1. These equations are good for long cylinder beams where L is greater than or equal to 8 the height of the beam. So L is the length of the beam and H is the height of the beam. So this is how we ensure or consider the beam to be long and cylinder. If L is less than 8H, you want to use the Timoshenko beam theory, not the Bernoulli Euler beam theory. And the stiffness matrix of the beam, K, of course, is given by this term here as a 4 by 4. Okay. Since we were able to find the element stiffness matrix, of course, with respect to the local axis, we can start using that to solve some problems where everything is oriented along one axis. So this is what I plan to do on Thursday as an application. Okay. Any questions? We're good? Okay. You're talking about homework 3, due date? It's February 25th. If we have not finished the material, you cannot do the homework. Okay, so we'll make sure that we push the homework until we finish all the material. And I will revisit the dates accordingly and make sure you are all well prepared before the first exam. Okay, I know we are preparing for the first exam. I'm hoping that we have it before the spring break while it's still fresh, or would you rather have it after spring break? Before, so you can enjoy the spring break, right?
Yes.
Okay. So let's push towards that. Okay. I'll see you all on Thursday.